So we come to chapter 6 and section 6.1, talking about probability distributions. Now this is a really important section, and I'm hoping that particularly these videos are going to be helpful here, because a big problem is caused by people not getting the right idea of what we mean by a random variable and what we mean by a probability distribution. And it's one of those things that is very difficult to get your head around the first time, because it doesn't seem sort of important in some ways to worry about the distinctions. And then you find later on, when you're on chapter 7 or later on in this chapter, or even on the second year of the course, there's a problem, you don't quite understand what's going on, and often the fix is to go all the way back and make sure you've got the right idea of what a random variable is. So we might find that this is a useful video because you've seen this in lessons, and this is where we're coming back to. So the first idea then is, what is a random variable? Well, you've seen tables like this from GCSE sort of questions or like this. So we are putting, in this case, we're rolling a dice, and the dice can take the value 1, 2, 3, 4, 5 and 6. And with those probabilities, on a GCSE paper, they'll often have a question, something similar, you know, a spinner can take the values 1, 2, 3 and 4, and probability it takes a 1 is 0.1, probability it takes a 2 is 0.7, probability it takes a 3 is 0.1, so what's the probability that this spinner takes the value 4? And you've got to work out the missing number. It's those sorts of questions we're thinking about. So the random variable, it's very difficult to come up with a definition that's not entirely wrong. The best I can do is the following. It's all the possible outcomes of the experiment. Now, if you look here, that's the same definition as a sample space. So a random variable is sort of all the outcomes of the experiment, and it's also sort of the result of the experiment at the same time. So it is the top row of this table. There are all the outcomes of the experiment. But on the other hand, we talk about the random variable as taking one of these values. So we'll say, what's the probability of the random, you know, if I do this experiment, rolling a dice, see what number comes up. If the number is a 3, then I say the random variable takes the value 3. So it's the thing which takes the value which is the result of the experiment. That's actually a good definition. It sounds like we've not really defined it there, but that's a good definition if you can get through the grammar of that. It's the thing whose value is the outcome of the experiment. I do the experiment. What was the outcome that I got? The random variable is the thing which takes that value. Another way of thinking about that is that it's represented in the top row of the table, and it takes a value from the top row of the table. It's the thing that can vary, a variable. It varies through all of these values. Okay. Now that's the way I'd define it. I know there's a lot of words there. It seems like a definition which is sort of 5 minutes long, but the definition is this is the best way I've come up with so far, and I'm still working on my definition to make it as clear as I can to people that I teach. But I think the best way I've got of thinking about it is, think about it as simultaneously all the outcomes of the experiment, so everything in the top row, and the actual result of the experiment. It's the thing that takes the specific result, which is the result of the experiment. If you roll the dice and get a 3, the random variable's just taken the value 3. Before you actually roll the dice, the random variable could take the values 1, 2, 3, 4, 5 or 6. Okay. Now, and I have a slight problem, if I can just find it. A random variable. Now, a random variable is a variable whose value depends on the outcome of an event. That's fair enough in the definition in the book, but it does say here the variable is random if the outcome is not known until the experiment is carried out. Now I have a slight qualm with the book's definition of random variable here. Random, remember, in statistics should mean everything's got an equally likely chance of happening. So in this case, we roll that dice, all of those outcomes are random. If the bottom row of the table, though, has the probabilities in it, and those probabilities aren't all the same, then these, sorry, I don't know if you can hear my small child screaming in the background. These probabilities, these outcomes happen with a different probability, so they don't happen at random. There's not an equally likely chance of getting a 1, 2, 3 and 4. So the word random, in the definition of what a random variable is a bit of a problem. It's a bit of a false friend there. A random variable doesn't take values at random. It takes values with probabilities which are defined by the bottom row of the table. Okay, so random variable, the outcomes of the experiment. Sample space is just a list of all the outcomes of the experiment. So a sample space and a random variable in some ways quite similar. We should hopefully be all right with the word discrete. That's so if the outcomes of the experiment are discrete data, then we have a discrete random variable. And the other important definition here is this probability distribution, which is the bottom row of the table. So once you know what the outcomes of the experiment are, you know the values that the random variable can take, then we need to say, well, what's the probability of the random variable taking those values? Now, if we have a discrete probability distribution, we can draw it in a table like this. And by the way, if we have a discrete random variable, we can draw a table like this. And everything from this book, everything on the first year course at A-level, is going to be a discrete random variable. So for this one here, let's look at it lower in the example when they've actually worked out the probability distribution. We can take the value 1, 2, 3, or 4 with these different probabilities. Okay. With this experiment over here, rolling a dice, we can take the values 1, 2, 3, 4, 5, or 6 with these probabilities. And in this case, because we're rolling a dice, it's a fair dice, the probability of getting 1, 2, 3, 4, 5, and 6 is equal everywhere. Okay. So the fact that we used GCSE, and which is sort of intuitive, is that the numbers in the probability distribution have to add up to 1. If the only options are 1, 2, 3, and 4, the probability of getting a 1 plus the probability of getting a 2 plus the probability of getting a 3 plus the probability of getting a 4 has to be 1. You're certainly going to get 1, 2, 3, or 4 if those are the only possible outcomes of the experiment. So as far as a sort of technical mathematical definition is concerned, a bunch of numbers that add up to 1 is sort of fair enough for a probability distribution. But as a slightly more practical statistical definition, when we know what the outcomes of the experiment are, when we can give each of those a probability, the probabilities, the bottom row of the table, give us the probability distribution. A little bit of notation. A random variable tends to get a capital letter, usually a capital X, if we haven't already used a capital X earlier in the question. So that's the random variable. The little x is the sort of individual values. So if I talk about the probability of the random variable x equaling little x, I might be saying something like, what's the probability that the random variable x equals 3? What's the probability that the random variable x equals 4? That's the same as saying, what's the probability that the outcome of the experiment when we actually rolled this dice was 3? What's the probability that when I actually rolled the dice I got a 4? And this table in the top row represents all of the values. So I say, well, little x is 1. So what's the probability of the random variable equaling little x when little x is 1 is 1/6. What's the probability? Well, what's the probability of the random variable capital X equaling little x when little x equals 2? That's 1/6. So that's how we read those tables there. And then you can picture that on a little diagram like this, just a little sort of bar chart, only instead of bars we're putting lines on them. Just and this will come in handy a lot later. Not a lot later. It will come in handy a lot later when we get to section 6.2. Just picturing your distribution like this. Each of the outcomes on the x-axis, and the height of the bar just represents the probability of that outcome happening. Okay. This is the fact we've already discussed. The probabilities all have to add up to 1. And then we can use that in questions like example 2, where we're given a function. It tells us the probability of the random variable taking the value little x is equal to k divided by x. So when little x equals 1, probability that random variable takes the value little x is k divided by 1. For 2 it's k divided by 2, for 3 it's k divided by 3, and so on. Okay. Now, have you noticed there's no it says this is based on a 4-sided dice, but there's no particular way of picturing this dice. It doesn't feel like a very probability sort of a question here. This is a question completely made up for this example. I can't think of why a dice would have a smaller probability of getting the 4 than it would of having the 1. I can't imagine how you would shape the dice so that it's more likely to come up 1, a little bit less likely to come up as a 2, a little bit less likely to come up 3, a little bit less likely to come as a 4. That's a very oddly shaped dice, and it's not one that's sort of intuitive to deal with. The point of this question is they've made up a situation so that they can test whether we understand the facts and about the probability distribution. And the only fact we need to know so far is that these 4 numbers have to add up to 1. So it's a little bit of an unfair example because it doesn't help our intuition at all. It's almost easier if you just think of it as a purely theoretical example. This is a random variable that can take the 4 values 1, 2, 3, and 4 with these probabilities, and what we know then is if you add those probabilities up, they must equal 1. If we do add those probabilities up, we get an equation which has just got a k in it, so we can find out what k is. Once we've got k, we can work out those probabilities. We can also ask the questions like this: what's the probability the random variable takes a value bigger than 2? And if we've got the table, we can just read those values off. Bigger than 2 would be taking a value 3 or 4, so we add those together. Between 1 and 4, not including 1 and 4, in this case is the same as probability of taking value 2 or 3. And so we add the probability of 2 and the probability of 3 together. The probability of it taking a value bigger than 4, it can't, the highest value that this experiment can take as an outcome is 4. And I think the only thing to add for this section is this notation here, which first comes in example number 1, so let's just deal with it down here. It may be a function notation that you're not quite familiar with, so let's just have a quick look at it. If you look at it, it's fairly intuitive, I think. So in this case, we're tossing 3 fair coins. All the possible outcomes are listed here. Just by working it out, you can get a heads first and then 2 heads, head first and then head tail, head first and then tail head, head first and then tail tail. And then all of those same things, instead of getting a head first, you get a tail first. So just all the possibilities listed. How many heads did you get? You could get 0, 1, 2 or 3 heads. We've got a list of the full sample space here, and all of those outcomes are equally likely, so we can work out that 1 out of 8 gives us no heads, and so on. So we can work these things out. So if you look at this table and look at this function, you can perhaps get the idea of the way this function is working. The probability that the random variable capital X takes the value little x is 1/8 if little x is 0 or 3. Is 3/8 if little x is 1 or 2. Okay, so what's the probability that the random variable x takes the value 2? I look for a 2 over here. There we go, if x is 2. The probability that the random variable takes the value 2 is 3/8. Or in other words, the probability of getting an outcome of 2 on this experiment is 3/8. We always have to include this otherwise, because we're thinking of this as though it's a function. Well, in fact, it is a function. So we need to say what happens to the rest of the inputs. So if I input a, what happens to the rest of the little x values? Okay, so if x is 0, 1, 2 or 3, I get an output. If the input is anything else apart from 0, 1, 2 or 3, the output is 0. The probability of getting any value other than 0, 1, 2 or 3 is 0. And that really is everything to say on section 6.1.